guys who were up to no good started making trouble in my neighborhood. I got in one little fight and my mom got scared and said, "You're moving with your auntie and uncle in Bel Air." I begged and pleaded with her day after day, but she packed my suitcase and sent me on my way.
Oh, welcome, ladies and gentlemen. Happy Monday night, and perhaps you recognize that theme song from my favorite television show growing up. So I might be going back a little too long ago, but if you remember that TV show, give me a holler tomorrow. I'll be impressed. Our first title today, we're going to do 3 mini titles. Our first one is called The Properties of Radicals. And the first thing, we're going to start to, we've looked at a lot of square roots, but we're going to start to look at cubed roots and fourth roots and fifth roots and so forth. The general form is, we're going to say the nth root of radical k. Now the n is a tiny little number that we have inserted inside the radical. And the special name for that number, for the letter n, we call it the index. The index. So that is what letter n is called. And then k is what we call the radicand. Kind of another fancy name. But it's very important that we all have to use the same terminology so that we can, communicate mathematically and all understand what each other's trying to talk about. So we're talking, n is the index, k is the radicand. Now, as far as the product property of radicals, we're saying that the nth root of m times n can be broken into smaller pieces, such as the nth root of m times the nth root of another number called n. We've actually used that property a lot. For instance, when we simplified the square root of 8 and broke it into radical 4 times radical 2, we were using this property all along. We're just going to continue to use it with higher roots and so forth. And similarly speaking, the quotient property says that if you're trying to take the nth root of, I'll mix up the letters this time, we'll say a divided by b. We're allowed to break that into smaller pieces as well, such as the nth root of a divided by the nth root of b, and then we could simplify from there. For instance, just to review, we've talked about simplifying things like the square root of 32, and we would have looked at our list of perfect squares, and we would have asked ourselves, what's the biggest number on this list of perfect squares right here that divides nicely into 32? You might say that 4 divides into 32, and I would agree with you, but I would also counter with this idea, is it the biggest number on that list that divides into 32? And hopefully you'll recognize that 16 is the biggest number. Now 16 times what? 16 times 2, and our property on the last slide said that that could be rewritten as radical 16 times radical 2, which then simplifies to just 4 radical 2. Now what we're going to start to do now is look at, instead of looking at perfect squares, we're going to graduate to the next level and we're going to start to talk about perfect cubes. And here's another list that we're going to have to become very, very familiar with. The first number on my list of perfect cubes, well, let's see, 1 raised to the third power is 1, 2 raised to the third power is 8, 3 raised to the third power is 27, 4 raised to the third power, 4 times 4 more would give us 64. And let's do one more. 5 to the third power, 5 times 5 times 5. Let's go with 125. Those are the 5 perfect cubes that I want you to become really, really comfortable with. Now, when I say perfect cube, I'm referring to the 1, the 8, the 27, the 64, and the 125. Those are my perfect cubes that I want you to know inside and out. So keep that list of numbers fresh. Let's try to simplify a couple perfect cubes. Let's look at the cubed root of 32. And I want you to really work on your handwriting. When you say cubed root, I want to make sure that 3 up here is very small and it fits right inside the lip of that radical. Now we're going to go look at our list of perfect cubes that we just said. We said the perfect cubes were 1 and 8 and 27 and 64 and 125. Which number on this special list right here is the biggest number that divides into 32? Hopefully you recognize that 8's the biggest number. And we're going to say, whoops, scratch that. I wanted to write the cubed root of 8 times 4, which could be rewritten as the cubed root of 8 times the cubed root of 4. And the cubed root of 8 is 2 times the cubed root of 4. And that is, believe it or not, that is my most simplified answer. Now, of course, if that was the square root of 4, we could simplify more, but the cubed root of 4 cannot be simplified any further, and this was exactly how we would write our final answer. Let's take one more look at an example where we'd simplify with perfect cubes. I want to try the cubed root of 54. So we ask ourselves, we look at this special list over here, and we ask ourselves, what number on that list is the biggest number that divides nicely into 54? Hopefully, with a little bit of luck, you came up with 27. So we could say cubed root of 27 times 2, which then becomes the cubed root of 27 times the cubed root of 2. And the cubed root of 27 is just 3 times the cubed root of 2. So 3 times the cubed root of 2. That is my final simplified answer. Well, now that we've just refreshed our memory on simplifying radicals, we want to graduate to adding and subtracting radicals, and it's a very friendly topic. I think you're going to feel really comfortable if you feel comfortable with saying that 3x plus 2x is 5x. Then you're going to totally feel comfortable with adding and subtracting radicals. Because we could simply say something like 3 radical 5 plus 2 radical 5 is 5 radical 5. You'll notice all we're doing in both of these examples, whether there's x's or radical 5s, is we're focusing on the coefficient. We're taking the 3, we're adding it to the 2, getting a total of 5, and the variable, whether it be x or the radical 5, is not changing. It's kind of coming along for the ride. Just like asking yourself, 3 apples plus 2 apples is, of course, 5 apples. And we could flip this around. Of course, 7y minus 3y gives us a grand total of 4y. Similarly speaking, we could say 7 radical 2 minus 3 radical 2 is 4 radical 2. So let's see if we can come up with some general guidelines here for adding and subtracting radicals. So here are my 2 main guidelines to live by when you're adding and subtracting radicals. Number 1, we want to get in the habit of simplifying each individual radical first. Once you get them all completely simplified as individuals, now we're going to focus on combining only the like radicals, which is a fancy way of just saying like terms. For instance, we mentioned earlier that 3 radical 5 and 2 radical 5 were like terms, and therefore we can combine them. Now, if I had asked you to add 3 radical 5 plus 2 radical 7, now there's nothing you could do on that problem. Because we do not have like radicals, aka we do not have like terms, I cannot add those terms. That would be my final answer in essence, since I can't combine them. But let's move on. We'll take a look at a couple problems where we will find some like terms that we can combine. The first example I want to try to add and combine is, let's do radical 12 plus radical 8 minus radical 72. Notice all of these are square roots, which are a little friendlier. And at first glance, we would say that we don't have any like terms, we don't have any like radicals, and so we can't combine any of them. But again, refresh your memory with what we just wrote down as our first step. We want to simplify each individual radical by itself, and 12 is divisible by 4 times 3. 8 is divisible by 4. We could say radical 4 times radical 2. And last but not least, 72 is divisible by 36, and we could say radical 36 times radical 2. The first term becomes 2 radical 3 plus 2 radical 2 minus 6 radical 2. And out of the 3 terms, we can actually combine the second one with the third one. However, we cannot combine either of those terms with the first one because we had different radicals. So as my final answer, I'm going to suggest that 2 radical 3 plus a negative 4 radical 2 is my final answer. Or maybe more concisely, we could say 2 radical 3 minus 4 radical 2 is our final answer. And it looks like that. Let's try another one. Let's try 8 radical 80. So now we're going to throw some coefficients in front here. Minus 6 radical 20 plus 2 radical 45. And hopefully I got enough room here to finish this one. But the 80 is divisible by 16 and 5. The 20 is divisible by 4 and 5. Notice I like to put the perfect square first and the non-perfect square second. And last but not least, 2 times. I'm going to break it into radical 9 times radical 5. Now you notice as we look at this first term, it says 8 times radical 16. Emphasis on the multiplication there. And we all know that radical 16 is a 4. So we're really asking ourselves to multiply 8 here times a 4 there. Gives me 32 radical 5. Minus, this says 6 times radical 4, which is really 6 times 2, giving me 12 radical 5. And then, let's see, 2 times radical 9 is really 2 times 3, which is 6. And we've got 3 terms, and they're all like terms, so we're going to focus on just the coefficients. 32 minus 12 gives me 20, plus 6 is going to give me 26 radical 5 as my final answer. Our last example with adding and subtracting involves cubed roots all of a sudden. Let's take a look at the cubed root of 8x plus the cubed root of 16x plus the cubed root of 27x. So, and the one thing I want to plant in the back of your mind right now is as we work through this problem, we've got to continue to write cubed root each and every time. We've got to remember that our little index is a 3. If we don't throw the 3 in there, then it's going to appear as if it's the square root, and that would totally change the problem. Now, as I look at this first term, I'm going to break it into the cubed root of 8 times the cubed root of x. Why did I do that? Just refresh your memory, go back in your notebook, look at that list of perfect cubes we generated a few minutes ago. 8 is actually a perfect cube. It's not a perfect square, but it is a perfect cube, and therefore we broke the 8 and the x apart. Plus, now 16 is divisible by 8, so I'm going to say cubed root of 8, that's the biggest perfect cube that divides nicely into 16, times the cubed root of 2 times the cubed root of x. And last but not least, I'm going to say 27 itself is a perfect cube, so I'm just going to break that into cubed root of 27 times the cubed root of x. As we try to simplify each of these terms, I'm going to say in that first term, the cubed root of 8 is just a 2, so 2 times the cubed root of x is the first term. Again, the cubed root of 8 becomes a 2, but then these two terms, I'm just going to multiply them together into 1 and say cubed root of 2x. If you don't want to break those two apart in the first place, I have no problem with that whatsoever. And then moving to our last term, we could say the cubed root of 27 is simply a 3, and then the cubed root of x comes along. As we step back and we ask ourselves which of these 3 terms are like terms, I think you'd agree that the first term and the third term, those are my like terms. They have the same radicand, so therefore I can add their coefficients and I'll get 5 cubed root of x. But then this bear right here is kind of the odd duck, and he just kind of comes along for the ride. The reason I cannot combine him with the other terms is that we had a different radicand. That's the quantity right there underneath the radical sign. And so here is my final answer. And that does it for adding and subtracting. We have one more mini title here, and that's called multiplying. Let's go try some multiplying. Well, our last stop of the day is with multiplying radicals, and I think, again, you're going to find this to be a fairly friendly topic. Earlier today, we had a property on the first slide that said the nth root of, I believe we used m times n earlier. I wish I would have used a times b, just to use some fresh letters, but we said we could break that into the nth root of a times the nth root of b. We're actually going to turn that property around now when we're multiplying, and we're just going to basically do the reverse. We're going to say that the nth root of a times the nth root of b can be written as the nth root of ab. One of the things you'll notice here is in order to be allowed to multiply radicals is we've got to make sure that this term has the same index as this term does. And for example, if we have a square root here, we have to make sure that we're multiplying by a square root. Or if we have a cubed root here, we have to make sure we're multiplying it by another cubed root. Otherwise, it's an illegal operation. So our first example is simply asking us to take radical 6 and multiply it by radical 5. You'll notice both of these factors do have the same index. There's an invisible 2 right here, and then there's an invisible 2 right there. And thus, we could write radical 30 as our final answer. Another quick example, if we wanted to do the cubed root of 4 times the cubed root of 10, we have the same index, therefore we're allowed to multiply these numbers together and say the cubed root of 40 It's always a good habit to, before you think you're finally done and can move on to the next problem, ask yourself, can this be simplified? In other words, is 40 divisible by any perfect cubes? Make sure we're looking at the list of perfect cubes, not perfect squares. And I think that 40 is divisible by a perfect cube, namely 8. So I'm going to rewrite that as the cubed root of 8 times the cubed root of 5. And my final answer would be 3 times the cubed root of 5. Why is the cubed root of 8? Whoops, that's not a 3. That should be a 2. I hope you guys were thinking that something was wrong there. Yes, cubed root of 8 is 2 because 2 raised to the third power equals 8. And right there's our final answer for number 2. Okay, our third example. What if we wanted the fifth root of 8 times the fifth root of 5? Again, we have the same index, therefore we are allowed to multiply this number 8 by this number 5, and we would say our answer is the fifth root of 40. Now, we haven't officially discussed a list of perfect fifth powers, and we'll get to that in a couple days. But again, we would challenge ourselves, ask ourselves, is 40 divisible by any perfect fifth powers? And so we'll take a look at that later in the week. Our fourth example asks us to do the 3 times radical 7 times 4 radical 11. We do have the same index again. Both of the indexes are an invisible 2. In this situation, we're going to multiply the coefficient by coefficient. 3 times 4 gives me a new coefficient of 12. And as far as the radical goes, radical 7 times radical 11 is radical 77. And there's my final answer. Number 5. Let's do 3 radical 2 times 4 radical 10. Again, we've got the same index, so we're allowed to multiply. Coefficient times coefficient gives me a 12. And then radicand times radicand gives me a radical 20. Are we officially done with that problem? Not quite. When I look at the radical 20, I think of radical 4 times radical 5. This radical 4 is really a 2. Therefore, 12 times 2 is 24. And the radical 5 comes along for the ride. 24 radical 5. Okay, we're gradually building up to some slightly more complicated multiplication examples. Let's do radical 5 times the quantity 3 radical 6 plus 12 radical 3. You'll notice we've got a monomial on the outside here and a nice binomial on the inside here. So we're going to take advantage of our distributive property. We're going to do radical 5 times 3 radical 6, and then eventually we'll do the radical 5 times the 12 radical 3. Now just to confirm, we do have a coefficient in front of the radical 5, although you don't see it. There is essentially an invisible 1 in front of that radical 5, if that helps you think about this problem. So 1 radical 5 times 3 radical 6 is going to be 3 radical 30. Notice we multiplied the coefficients 1 by 3 to get 3, and the radicand 5 times 6 to get a new radicand of 30. Then we're going to redistribute. 1 radical 5 times 12 radical 3 is going to give me 12 radical 15. And then I believe that is as far as we can go. You'll notice that we do not have like terms, we do not have like radicands, and so therefore we are not allowed to add those two terms together. Let's try, let's see if we can squeeze one more in on this screen. Let's do the quantity 3 plus radical 3 times the quantity 2 minus radical 6. Now you'll notice this time we have a binomial in the first grouping and then another binomial in the second grouping, and therefore this problem is screaming FOIL. We're going to have to do first, outer, inner, and last to get through this problem. So first times first. 3 times the 2 gave me a 6. My outer terms would be 3 here times a radical 6 over there minus 3 radical 6. Inside times inside is going to be plus 2 radical 3. And last times last is going to be negative radical 18. Okay, ask ourselves if any of these four terms can be simplified. I believe that very last term is the only one that could be broken down into smaller pieces. I'm going to do radical 9 times radical 2. And of course, that radical 9 is really just a 3. So now we say, okay, I believe, oh my goodness, I can't believe none of these four terms are like terms. So we could say that 6 minus 3 radical 6 plus 2 radical 3 minus 3 radical 2 is my final answer. That's one of the uglier final answers you'll ever have, but truly none of them were like terms and there was nothing we could do about it. Okay, let's do 2 more examples. My 8th example wants us to take 2 plus radical 2 and multiply it by 5 minus radical 2. And again, we have 2 binomials, and again, hopefully you recognize that this problem is screaming for some foiling. And I would encourage you to maybe hit the pause button and try to foil this one out yourself, and then come back, hit the play button, and see if you have a similar answer as I do. Let's see. First times first gave me 10. Outside gave me negative 2 radical 2. Inside gave me positive 5 radical 2. And last times last here gave me negative radical 4. Now, that last term, when I said radical 4, you could have skipped that part and just said, you know what, that's a minus 2 right there for that last term. You can go as fast or slow on that as you want. Now, as far as combining like terms, I could say that my first term and my fourth term are like terms, and they give me 8. And then my 2 terms here in the middle are like terms, which gave me 3 radical 2. So 8 plus 3 radical 2 is our final simplified answer. Okay, one more example here. Let's do 4 plus radical 3 times 4 minus radical 3. Now your first instinct might be to say, yes, we've got 2 more binomials, so I need to FOIL again. But here's the good news. Perhaps you recognize that these 2 binomials were, yes, conjugates of each other. And because they're conjugates of each other, we're allowed to skip the O, skip the I, and we are going Florida style. First times first gives me 16. Skip the outer, skip the inner, and last times last gives me negative radical 9. Of course, that radical 9 is just a very simple 3. 16 minus 3 gives me a final answer of 13. And it's hard to believe that you could start with 2 binomials as ugly looking as these guys up here and get such a clean, nice answer such as 13. Well, ladies and gentlemen, there's our notes on simplifying radicals, adding, subtracting, and multiplying them. Now, as far as the simplifying goes, we didn't get too deep into it today, and our next couple of videos will get deeper into the simplifying part, especially when we have higher powers and more variables underneath that radical sign. But today we got off to a good start. Feel free to replay this as many times as you need to, and I encourage you to take very, very detailed notes. We'll see you tomorrow.